to kind of confirm that my audio was working properly. Got it. Let's see. Testing, set the meeting. Hit done and share. Greetings, scholars. Welcome. Let me see. So we're pretty much there, right? This is it. This essentially is the last of the new materials. So today we're going to be going through section 9.5 on the binomial theorem. As far as announcements, we are pretty much in the home stretch, right? So I can't stress enough that there's a hard deadline of May 1st, which is about 2 weeks out, right at exactly 2 weeks out. May 1st at 11:59 p.m. Everything on Pearson is going to lock out. I think we've had 3 exams that's available right now. Any assignment that's on Pearson, you can still earn up to 90%, right? You get unlimited attempts and there's only a 10% late penalty. So there's an automatic extension built into everything. So if you want an A on any assignment, you can still do it right now. Also, if you don't go back and do anything else, you definitely want to make sure that your exams are in order. That's going to be the bulk of your grade. It's like 80% of your grade. And yeah, I can't really think of anything else. As usual, if you have questions, comments, or concerns about anything, feel free to unmute yourself to get my attention. Also, feel free to use the chat. I do check the chat periodically, but for a faster response, you would just want to unmute yourself. So today's presentation, it's supplemental material. I don't think it's in our text, so this is coming from another book. I've already assigned homework from this text, right? So all you really got to do is just log into Pearson and kind of complete the assignment like you've done everything else. And I'm pretty sure I included some of these questions on the final, right? So this will serve as the last of the new material. And then I think we'll have, again, like right at about 2 weeks, which is like 4 meetings remaining. So what I was thinking is that for those last 4 meetings, basically, essentially doing like a chapter, one exam per meeting, right? So like the first time we meet, we can review exam 1 as much as possible, then exam 2, exam 3. And then maybe I might have like that last meeting might be like some other kind of activity. And try to see, can we find some mathematical stuff in gaming or whatever, do something fun just for that last one. I will see. And if you remind me and hold me to it, more than likely I'll do it, especially if we've done all the things that we need to do, okay? And as usual, I'll check the chat again just to kind of get the stragglers. I'll check it in like 5 minutes. So I am live streaming this to YouTube, so I do intend to kind of finish the lecture. I feel like it's a rather short lecture. I hate to get you guys' hopes up. I usually try not to make that statement and then students be like, oh, we're gonna get out early. Even though this is, I know how our structure is, but it is what it is, okay? Let's see. So today, we're going to be looking at chapter 9 from this text. I use a pre-calculus, a unit circle approach by Rodney Waters, the 3rd edition. And this is a further topic in algebra. This is section 9.5 covering the binomial theorem, right? So a few objectives. 1, we like to use Pascal's triangles to compute binomial coefficients. 2, we like to use Pascal's triangle to expand the binomial power. 3, we like to use the binomial theorem to expand the binomial power. And then 4, we like to find the coefficients of a term in a binomial expansion, right? So when you see the phrase binomial, right, in this context, bi meaning what? 2, and nomial meaning like a name or a term, right? So these are 2-term expressions. And so basically we're going to be exploring like, this is something like if you had x plus y quantity squared, right? And so in the past, you might use something like FOIL, first, outer, inner, last, or you might make sure that each term, it's basically just the expansion of a binomial. Okay. So I'll grab this and go like this. And I'll just keep an eye on the time. So binomial expansions, part 1 of 3. It says the patterns for expansions of a binomial raised to some power n, again, binomial because we have 2 terms, raised to some integer exponent, where n is 1, 2, 3, 4, 5, basically a positive counting number, right? It suggests the following. So if we're expanding something like this, the expansion of this has n plus 1 terms, right? So think about if this were 2. If that were squared, you would finish, you essentially 3 terms, right? I mean, there are some times when you expand it where it's still 2, but and it, like if that was squared, you would finish with the trinomial, right? So we've done that extensively. We can at least confirm a case. It says the sum of the exponents x and y in each term equals n. So if we add up the exponents, the sum of exponents on x, y in each term add up to n, right? So for 2, the sum of the powers in each term, they all add up to 2. The exponent on x starts at n in the first term and increases by 1 for each term until it reaches 0 in the last term. And then there's an analogous for y, right? So y is going to start at 0 and increase by 1. So the exponent y starts at 0 in the first term, and then increases by 1 for each term until it reaches n in the last term, right? So this is just backstory. I know this might sound like a lot of jargon, maybe, but I feel like when we start working a few examples, I feel like it'll become more clear. The variables x and y have symmetrical roles. That is, replacing x with y and y with x in the expansion yields the same terms, just in reversed order. Okay. Binomial expansion is 3 of 3. You may have also noticed that the coefficients of the first and last terms are both 1, and the coefficients of the second and the next to last term are equal. In general, the coefficients of x to the n minus j, yj, and xj n minus j are equal, right? For j equals 0 through n. The coefficients in the binomial expansion of x plus y to the power of n are called binomial coefficients, right? So let's just, you'll see, like basically it's just talking like about the symmetry. When you expand the binomial, you'll notice a lot of patterns and symmetries and similarities between the terms. So, we want to extend this notion. Let me see the clock. Extend this notion of expanding a binomial, and the first application we want to look at is Pascal's triangle. So when expanding x plus y to the power of n, the coefficients of each term can be determined by using Pascal's triangle, right? So the top row of the triangle, which contains only one number, represents the coefficients of x plus y to the power of 0, right? And it's referred to as the zeroth row. The next row, called the first row, represents the coefficient of x plus y to the power of 1. Each row begins and ends with 1, and then each entry of Pascal's triangle is found by adding the 2 neighboring entries in the previous row, right? So let's just see it in action. I mean, yeah, this is fine. So essentially what's going on, you start with the 1, and then that's row 0, and then on row 1, so basically you kind of start with like these 3, right? You have 1, 1, 1 in a triangle like that. So then whenever it's on the end, it's a 1, right? So on the outer skirts, it's a 1. And then to get this number, basically 1 plus 1 gives you 2, right? To get this 3, 1 plus 2 gives you 3, 2 plus 1 gives you 3, and then the last number is a 1, right? So then to build the next row, first the 1 comes down, and then 1 plus 3 adds up to 4, 3 plus 3 adds up to 6, 3 plus 1 adds up to 4, and then you finish with the 1, right? Continuing with this pattern, you can build, again, this is like row 0, row 0, row 1, row 2, row 3, row 4, row 5, row 6, so on and so on. That makes sense. Let me check, zoom in. Go ahead and make sure I hit save. I think I saved it already. We build Pascal's triangle, right? So each of these rows basically serves as the coefficient in a binomial expansion. So when we expand binomials to a certain power, like for instance, we said x plus y to the power of 0, you're only going to have one term. That's going to be the coefficient. X plus y to the power of 1, these are the coefficients. X plus y squared, these are the coefficients. X plus y cubed, these are the coefficients. X plus y to the power of 4, these are the coefficients, so on and so on, right? So let's see this in action. We're asked to expand this. So suppose we wanted to expand this using Pascal's triangle. Let's do it using Pascal's triangle, since we just introduce Pascal's triangle, right? So since we have it to the power of 5, we need to get to the 5th row of Pascal's triangle, right? So here's row 0, and then here's row 1, and then 1, 2, right? This is row 0, row 1, row 2. We need 3, 4. We need to go all the way to 5. Okay. So then this one, you start with 1. 1 plus 2 is 3. 2 plus 1 is 3, and then you finish with 1. That's row 3. You start with 1. 1 plus 3 is 4. 3 plus 2 is 6. 4, 1. So then for row 5, we're going to have 1, 5, 10, 10, 5, and 1. Let me give myself some space. Is that when we expand this binomial, these are going to be the coefficients. So then the way we build it is the following, right? Let's see. So normally, here, let me offer this as a precursor. So if it were x plus y, let's kind of start by expanding this. X plus y to the power of 5. If we were to expand that, right, we would have x to the power of 5 times y to the power of 0. And then we're going to say plus, then, the x's count down. So you're going to have x to the power of 4, y to the power of 1, plus x to the power of 3, y to the power of 2, plus x of 2, 5, 4, 3, 2, y to the power of 3, plus x to the power of 1, y to the power of 4, plus x to the power of 0, y to the power of 5, right? So these are the terms. Notice that our n is 5, and we have a total of n plus 1 terms, right? So then let's go ahead and incorporate our coefficients, right? So from Pascal's triangle, like the coefficient of the first term, so there's a 1 here, right? There's a 5 here. There is a 10 here. There is a 10 here. There's a 5 here and a 1 there. That's from Pascal's triangle. So then all we need to do to expand our binomial, replace x, replace x with 4y. Let's go ahead and do the x's in blue, right? So basically what we're going to do, we're going to replace the x's with 4y. And then we're also going to replace what? Y. We're going to replace the y's with the negative 2x. So we're going to make those substitutions, right? And just to kind of help drive it home a little bit, I want this guy, that one, that one. That guy, that guy. All those x's with 4y, and then let's go ahead and do the y's. With the y's, we want this guy, that guy. Basically, we're switching those out, right? So if we put it all together, well, the one, let's just bring it down. So we're going to have 1 times x, which is now 4y, and it's going to stay to the power of 5. And then our y, which is negative 2x, that's going to stay to the power of 0, right? That's the first term. Then we're going to say plus. The 5 comes down. X is now 4y to the 4 is negative 2x to the power of 1, right? And basically we're doing those substitutions across the board, right? I'm running short on space, so I'm going to kind of continue on the far left. So then we're going to say plus the next 5 is 10. Let's just copy and paste. This consistent, and then this is 3. Let's go ahead and paste what we need, right? 6 of those, 1, 2, 3, 4. Them all as plus. So we got 1, 5, 10, and then 10, 5, 1, okay? And then let's go ahead and bring down our powers. So the blues are counting down, 5, 4, 3, 2, 1, 0, and the oranges are counting up, 0, 1, 2, 3, 4, 5. And then the final step after those substitutions is just, do your simplifications. For instance, 4 to the power of 5. I don't think I know that off the top of my head. Hey, Siri, what's 4 to the power of 5?
4.
4. 5. Plus, let's see. Hey, Siri, what's 4 to the power of 4 times 5 times negative 2?
Negative 2 is negative 2,560.
560. That could be the negative. Hopefully this is okay. Like, trying to figure something like out this on your own might be a challenge, but hopefully the way I presented it, it's okay. Then we're gonna have basically y to the 4 times x. Okay, I think that's okay. And then the next one, 4 times 4 is 16 times 4 is 40 plus 24 is 64. So then that's 640 times 2, 640, 1280. X squared, okay? 16, so then that's 160. Wait a minute, I think I made a mistake. This should be positive because it's squared, right? Oh, thank you, stop. Okay. Let's see. So 16, 160. 8 is 800 plus 480 is 1280. Ooh, let's see. We're gonna say minus. I might be getting some of these wrong. Y squared x cubed, but I think the point is driven home. 5 times 4 is 20 times 16. Man, everybody want to call me. 20 times 16, 300 and 320. 320 y x to the power 4. And that goes anything to the power of 0 other than 0 is 1. And that's going to be negative. I think the sign should alternate, plus minus, plus minus, plus minus. 2 to the power of 5 is what, 32? 32 x to the power of 5. I think that's the thing. Do like this. Let's go here. And I'm gonna just shrink all this down to kind of have it fit on the page a little bit better. And then we can check. Now there are faster ways to go about this. This example was more for instructional purposes or instruction purposes, just so you can see it and get the concept, right? So we got this. Let's see, how do we do? Let me copy this so we can just have it side by side. Let's copy. Yeah, I think I definitely got some of those numbers off. Let's paste. 2560 to 12. This should be another 2560. I definitely missed something there. But I mean, you get it. Obviously, I was doing it without a calculator. Okay, it wasn't too bad. It was just that one 2560. One to delete. And it was this one right here. This one's supposed to be pi to the third, which is this guy here. Let me see, 4 times 4 is 16 times 4 is 64, so that's 640 times 4. I think I did it times 2, so 640, yeah. So basically, this is multiply my answer by 2, and it should be positive. That wasn't bad. One error is not bad. And you can use a calculator, you know, and things of that nature. Let me check Zoom again. Okay, see. Yeah, that was pretty good. Okay. Pascal's triangle, we already got this from the triangle. So then again, if you expanded x plus y to the power of fifth, you would get this, right? We got that. And then basically what we do, we replace x with 4y, right? And then we replace y with negative 2x, right? So we went and did those substitutions and crunched the numbers as best we could. We would have done better if we used a calculator, but that's fine. But we got essentially the same thing. Okay. Oh, skip the slide. So then now this symbol, right? We have like basically it's like an N on top of an R inside an elongated vertically elongated set of parentheses. So this is called the binomial coefficient, right? This is you read this as N choose R. So this is a binomial coefficient. It's called N choose R. So if R and N are integers, where R is greater than or equal to 0 but less than or equal to N, then we can define this binomial coefficient N choose R is going to be N factorial divided by R factorial times N minus R factorial, right? So what do we mean by factorial? These exclamation marks, right? We're not screaming, we're not saying N divided by R times N minus R. No, that's not what we're doing, right? So so this exclamation mark, what it is called, this symbol is called factorial. And so what it means is you take that number given and then you say times you subtract 1. So like for instance, if it were 5 factorial, here, let's do like this. Suppose we were evaluating 5 factorial. 5 factorial means 5 times 4 times 3 times 2 times 1. So you say that number times the previous times the one before that, and you keep going until you get to 1. Suppose we did 7 factorial, right? That's 7 times 6 times 5 times 4 times 3 times 2 times 1, right? So that's what that symbol means. And then by definition, N choose 0 is by definition, that's 1. So, you know, because also by definition, 0 factorial is 1. That's just by definition, so that things can work properly. And so N choose 0 ultimately is 1, and then N choose N is going to be 1, right? And so when you apply these formulas with this definition, you get these 2 results, okay? So, you know, it's not obvious, and you would need someone to explain this to you if you've never seen this before, right? We use this kind of stuff in math. It's not all the time, but it definitely pops up, and you don't want to be caught. You don't want to be caught lacking or lagging? Lacking. I don't know if I subscribe to this YouTuber, but he was like, for today's subscriber challenge, you know, if I catch you lacking, then you have to subscribe. And he's like, if you intend to summon on this banner, then you got caught lacking and you have to subscribe. But if you don't intend to summon on this banner, then you get a pass. All right. So, but yeah, anyway, that's a fun little challenge that he does. It's just a quick little whatever. Okay. So that's the long and short on this symbol. Again, this symbol is called the binomial coefficient, right? And it's read as N choose R. By definition, is going to be N factorial over R factorial times N minus R factorial. And factorial means this thing here in purple. And then also by definition, 0 factorial is 1, right? So then because of this, these 2 hold. Okay. But this is called the binomial coefficient because it automatically gives you the coefficient of any term in an expanded binomial, right? You can jump straight to a term instead of trying to use Pascal's triangle because, we saw an example where we did the 5th row, right? And it was a little bit extensive. What if it was the 12th row or the 73rd row or the 10,000th row, right? You're obviously not going to do Pascal's triangle out that many times. So this is a elegant shortcut to jump straight to the coefficient of any term in Pascal's triangle or in a binomial expansion. Okay, that's what this is. So we're actually evaluate each binomial coefficient, right? Okay. So for part A, so then let me see. So for part A, 4 choose 1 means 4 factorial over 1 factorial times 4 minus 1 factorial, right? Let me see, 1 factorial is 1, 4 minus 1 is 3. So this means 4 times 3 times 2 times 1 over 3 times 2 times 1, right? So you should notice everything is multiplication and division, so we can cancel. This is canceled by this. So this first one really just boils down to 4. Okay. Choose 3. 5 choose 3. This by definition is going to be 5 factorial over 3 factorial times 5 minus 3 factorial, right? Be 5 times 4 times 3 times 2 times 1 over 3 times 2 times 1 times 5 minus 3 is 2. So then it's 2 times 1. All right. Now a lot of things cancel. Let's cancel what we can cancel. 3 to 1 cancels this 3 to 1. And then the 2 turns the 4 into a 2. So then 5 times 2, that means we're left with 10. Fit on one slide as well as best I can. Said, well, here, now we just said that like any non-zero choose 0, this answer should be 1. And I think this answer was also 1, right? But let's apply these to the formula and see them and expand it so we can confirm those results, right? So suppose we did 9 choose 0. So this means 9 factorial over 0 factorial times 9 minus 0 factorial, right? 0 factorial by definition is 1. So then this is really 9 factorial over 9 factorial. A number divided by itself is 1. This kind of, the last one is 35, choose 35. Out in like probability, like what you more than likely will have to take, like an intro to probability. But we use this is like combinatorics. This is like having n objects 3 different ways. Like say we have how many different ways can we choose, like in groups of 2, like in groups of R, right? Well, I know it's a little bit jumbled. Let me go ahead and do part D and then I'll clean it up. So if we did 35 choose 35, right? So this means by definition 35 factorial over 35 factorial times 35 minus 35 factorial, right? Minus itself is 0. 0 factorial is 1. So this is really just 35 factorial over 35 factorial, which is 1. Okay. Up to make it more presentable. Movie. I'm pretty sure that was way before your time. Yeah, Shrunk the Kids and that whole series. That was fun. That was like the vibe at that time was just so different. Things felt so different. the internet and like how we basically became like a global community has drastically changed like everything. Everything feels completely different. I'm not opposed to it, but it's and like another thing that's interesting to me, like, okay, I'm aware of like the time period before the internet, cell phones and internet and all of that. But I feel integrated with the internet. Like it doesn't really bother me that much. But then, but things feel different. Then it's like, well, dog, what is it going to feel like in like another 30 years? Like, what's going to be the next thing? And for me, honestly, my vote is for, I hope it's something like telepathy. Like, honestly, the direction that technology is heading, and it's basically what it is. It's kind of a long story. This is a tangent, and I'm just kind of like yammering right now. I see the time. I'm not going to keep you. I'm going to try to get you out on time. But for me, it's like technology, all it does, all it's done is like basically take our natural abilities and skill set and repackage it and package it back to us. But the reason I feel like we've lost these abilities is because we're distracted. We're completely disconnected. We don't do grounding. We don't tune into Mother Earth. We don't meditate. We don't take care of ourselves. So because we don't do these things, we don't take care of ourselves. We don't ground. We don't eat clean, we don't meditate because we don't do those, we don't have these abilities. That's just how I feel. I don't know if there's truth to this or not, other than just trying it myself. But the more I do kind of practice this stuff, it do kind of it gets closer and closer to stuff like that. But some of the stories are like basically all the things that this technology is able to do, that's actually what we're able to do. I've even seen the showcase. I had a professor when I was a student. He did a showcase where you know, he can crunch numbers faster than the calculator. Like you can spit out 347 times 256, and he'll spit out the answer faster than you can type it in the calculator. And so then if he can do that faster than the calculator, what else can we do faster and better than machines, right? And I'm like, well, and I asked him in that moment in time, like, how did you do that? And he wouldn't say anything, right? And so, but it's possible. I sat there and watched him do it, and like nobody could beat him. So then once you realize these things are possible, the next thing is like, well, how is it that people are doing this? So then you go on this quest to figure out, well, how are they doing it? And then once you figure it out, then you're able to do it. And then, either you pass it on to somebody else or you spark that interest in somebody else. And so for the next like 30, 40 years or whatever, the advancement of technology, if we're still here, if we survive singularity, that whole thing, where the robots becoming smarter than us and that whole thing. But basically, I think we're gonna like be going back to our abilities. Like one of the things I've seen is like you have this nanotechnology where it's implanted in people. I think it was some presentation on the Disney Channel, but basically it was giving people like there's this thing called hive mentality where everybody could communicate telepathically with the machines, even though if we cultivate it, we had that ability. But so now basically they're just taking our abilities, repackaging them through machines, and then selling it back to us. But then there's obviously it's fraught with pitfalls because if you got like nanotechnology inside your body, who's ever controlling machines, then who knows what they might do to us. If you've watched Black Mirror, those kind of series or whatever. Okay, this I found another these things. I'll put it with this brethren. Yeah, so even though I feel like the technology is going to keep advancing and it's really just going to reconnect us back to our natural abilities, but we just need it because we're distracted and we're lazy. But if we were less lazy and we actually took the time to sit with ourselves until we got it, I think these things would activate for real. And the reason my hesitation with the technology is because it's artificial. If you have a nefarious being in control of that stuff, and you don't want to have like artificial stuff inside your body where somebody has ill intent. So then at a whim, when they don't like what you're doing, or if you're misbehaving or not doing what they say, then who knows what they can do to you, right? So that's why I feel like it's more important to kind of cultivate your natural ability skill set than rely so heavily on the technology. But in the flip side, I do think it's important to be able to know how to use the technology and how to navigate it. But if it were up to me, I would be able to do that stuff naturally. Anyway, so that's the story time. We do have like right at about 3 minutes left in class. So I think I've only had like one person attend, which is okay. I mean, we're pretty much at the end of the semester, and you guys can access it. I do need to kind of track down and make sure that see who intends to finish it, and like I need to kind of follow up to see if like people need to be booted or whatever. But I know that you guys can access this recording, right? Because it's on my channel. So if you're in attendance right now, I'm going to go ahead and release you. I have a few more slides, or like right at about 10 more slides, and I'm just going to kind of keep going and try not to be so distracted, right? You know what I mean? Okay. That's dying. Let me go ahead and put this other. I said not get distracted, and I immediately got distracted by my headphones dying. But anyway, okay. Evaluate each binomial coefficient. Okay, so that was the one we just did. All right. So, and it should be 1 and 1, right? So I think we got the same results. Okay. So now we can take that binomial coefficient and apply it to this thing called the binomial theorem. So if n is a natural number, then the binomial expansion of x plus y to the power of n is given by the following, right? So remember, if we start with the variables, the variable x starts at the power n and counts down by 1 until you get to x to the power of 0, right? Over here, you have x to the power of 0. Y starts as y to the power of 0, and you add 1 to each exponent until you get to the power of n. And then your binomial coefficient, the top part is n, and the bottom counts up with the y. So it goes 0, 1, 2, 3 until you get to n, right? So it's all of this into this form, right? So this it's basically the sum as I goes from 0 to 1, 0 to n of n choose r of x to the power of n minus r times y to the power of r. So the coefficient n choose r of this is, again, this is what we literally just did, right? So I know it's a little bit all over the place. It's not as bad as it seems. Okay, let's work an example or two. Let's try to work an example. Find the binomial expansion of this guy, right? So if we apply that theorem that we just saw, right, the binomial coefficient is going to be what? It's going to start at 4, choose 0. We're going to have x to the power of 4. Let me think about it. I'm going to do it the way we did it initially because I feel like I can keep track of that a little bit better. Actually, I think I'm okay. And the next factor is going to be this negative 3y to the power of 0, right? Let's do the binomial coefficient in purple. So let me see. If we're going to the power of 4, that means we should have a total of 5 terms, right? So we did the first one. Plus, let's see, this 1. This would be what? 2. That would be 3. So now, let's do the binomial coefficient in purple. Coefficient is going to be 4, choose 0. Then we're going to have 4, choose 1. Thank you. Oh, we're going to have 4, choose 1 plus 4, choose 2 plus 4, choose 3 plus 4, choose 4. Right? That's not a 4. Right? And then our x's, let's do our x's in blues like we did before. So we'll do this term in blue. These are going to count down. So we're going to have x to the power of 4 plus x to the power of 3, x to the power of 2, x to the power of 1, x to the power of 0. And then our next factor, we're going to do that one in orange. So this negative 3y, that's going to count up, and we're going to do that one in orange. Okay. So then we're going to get negative 3y. Here, let me, I'm going to just copy and paste. 3y here, 3y here. And then again, these count up. So it goes to the power of 0, power of 1, power of 2, power of 3, and power of 4, right? Let me move these around. I think I'm going to try to get these on one line. Let's do this as well. X minus 3y. I'm going to shrink all this down to get it on one line, just because we can. Back as best I can. Let me, it looks a little bit slanted. Nudge it, so that's okay. I'm not gonna worry about that. Expand that original binomial, this is like basically the backbone structure. So now we need to kind of, simplify the different components. So this is going to be equal now. 4 choose 0, I think we said that that's going to be a 1, right? We're going to have our x to the power of 4. That orange part, any number other than 0 to the power of 0 is going to be a 1. So we could say, times 1 or whatever. And then we're going to say plus. 4 choose 1 is 4. You can confirm it by doing what we did earlier. We're going to have, let's be consistent with our colors. We're going to keep the x to the power of 3. Negative 3y. Terms. 2 kind of a shortcut for doing these combinations. Let's see, is 4 choose 2 should be the same as 4 times 5 over 2 times 1, right? If you do the formula, eventually you can get to a line like this. So then, you can get the result from there. A positive 9y squared. So we're still going to have to come back and simplify and combine like terms, right? Keep going. 4 choose 3 is, another way you can look at that is like 4 times 3 times 2 over 3 times 2 times 1, right? And that y term is what? Negative 27. 4 is I think that's an 81, a positive 81. Do one more step to simplify this. Is x to the 4. It's going to be a negative 12, x to the third y. The 10. 10 is what, 90? Four times 27, that's going to be negative. 4 times 20 is what, 80 plus 28 is 108, so a negative 108. So we get x to the 4 minus 12x cubed y. We got 90, it's supposed to be 54. Let's go back and fix that. 108 is good, and 81. How do we keep messing that one up? X squared, y squared. Three. 6. I think here this is supposed to be, no, that's a 4. Cool. Why am I counting up? I counted up. I think I'm just moving too fast. Right here, instead of counting down, I counted up. That's supposed to be 4 times 3. That's what I did wrong. Right there. 6. So then 6 times 9 is 54. Right? That's what I did there. For some reason, I counted up. Just moving too fast. Mistake. And it's 12x cubed y 50 plus 54x squared y squared minus 108 xy cubed. Okay. Text it really quickly. Mention 4 choose 0. You got 0, 1, 2, 3, 4. The x's are counting down. Right. Is counting up. Power of 1, 2, 3. At the same result. Okay. So it says the term containing the factor x to the power of r and the expansion of x plus y to the power of n. This term also contains the factor y to the power of n minus r. Okay, so this basically is how you find a specific term in a binomial expansion, right? Let me see. Yeah, I think this, yeah, find a specific or a particular term in a binomial expansion. So if you expand a binomial, how to jump straight to a specific term. Okay, so you have n choose n minus r times x to the r and then times y to the power of n minus r. Okay, let's see if we can see this in action. Find the term containing x to the power of 10 in the expansion of this, right? So let me see if I can just write what we just saw, that formula. Let me see. So if we had n choose n minus r, it was x to the power of r, and then y to the power of n minus r. Let's see. Let's see if we got that right. So again, the term containing the factor x to the power of r. So in our case, we have x to the power of 10. Okay, and so let's identify different components, right? Let's identify different components. So this is how we jump straight to a term. So in this case, our n is 15, our r is 10. Okay, x is x, and then y is 2a. Okay, so then if we want x to the power of 10, we want the term where x is to the power of 10. That means we're going to have y to the power of 15 minus 10, and we're going to have 15 choose 10, right? Okay. So 15 choose 10, You could start at 15 and go out 10 spaces. You can go like 1, 14, 13, 12, 11, 10, 9, 8, 7, 6. Let's see. How many is this? 2, 4, 6, 8, 10. All right, that's 10 right there. And then we could say divided by 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. All right. So then if we do, you know, we're still going to have our x to the 10, and now it's going to be what, y to the power 15, y to the power 5. Now we get a lot of things that cancel, right? They both have 10 through 6. That cancels 10 through 6, right? Let me see, 5 times 3 is 15, so that cancels this guy. 4 times 2 is 8. The 4 can turn the 12 into a 3, and the 2 can turn the 14 into a 7, right? So then the remaining part is going to be, let me see, 77. Let's see. Hey Siri, what's 7 times 13 times 3 times 11?
7 times 13 times 3 times 11 is 3003.
All right, I think that's what it should be. Okay, so this is how we jump straight to a specific term in a binomial expansion. Instead of expanding it all the way out and doing all this extra work, we have a way of jumping straight to a term. Wait a minute, but we need to replace the y with 2a. So let's go ahead and do that. So then one other thing, 3003, x to the 10, then we're gonna have 2a to the power 5. 2 to the power 5 is what, 32? Hey Siri, what's 32 times 3003?
32 times 3003 is 96,096.
All right, we forgot to substitute for y. Okay. So we get 96,096, x to the 10, a to the 5. Let's see, how do we do? 96,096, x to the 10, a to the 5. Okay. Okay. Oh, we're almost there. Ooh, good job. Okay. Oh, actually, we are there. Okay, so that was it. Yeah, so that was a showcase of like the binomial theorem, right? And we saw how, like, you know, we can get those coefficients from Pascal's triangle, but then we kind of explored this notion of the binomial coefficient, and then how to read it. It's basically, it's a combination, like n choose r, n objects taking r at a time with repetition. Long story short, we saw the formula for n choose r, right? So that was that n factorial over r factorial times n minus r factorial. We kind of saw some shortcuts there, and then we saw how to jump straight to a specific term in a binomial expansion, right? So if there aren't any burning questions, on that note, we're going to end the session here, and from one beautiful mind to another, enjoy the rest of your day. All right, guys. All right, take care. Enjoy your weekend. Peace.